So this is G485 homework booklet question 8. So we've got pass through an accelerator used to produce high-speed protons. The protons pass through an evacuated tube that's shown in the plane of the paper, and we've got the path of the photons there, we've got the radius, we've got the evacuated tube. State clearly the direction of the magnetic flux density B, the field in other words, that produces the circular motion of the protons. So I'm going to be using Fleming's left-hand rule. Only things I've got to think about are my force, directions of my force. Well, the direction of the force must be towards the centre of the circle, and I've got to think about the direction of the current. Well, because it's a positive charge, thankfully that's very, very easy. The direction of the current is in the same direction as the direction of the motion. If it was electrons, the current would be in the opposite direction to the direction of the motion, or anything else negative. So because I've got positive charge, the current and the direction of the motion are the same thing. So I just need to line up my left hand thumb in that direction, my left hand second finger for current in that direction, and I end up with my first finger pointing straight into my eyes, coming perpendicular up out of the paper. So there's A, perpendicular out of the paper. Show question. Okay, so ideally, certainly if we had a bit more space, we'd have said that the magnetic force on the particle is the only force, is the net force, and therefore is the centripetal force. So I've got mv squared upon r, centripetal force. I have used the capital R here, although it's not standard in the equation because they've told me that's the radius, is equal to pqv. Rearrange that, we get one of those V's cancelling off. We get, what else do we have going on? Yeah, that's it. Then I just need to multiply R, shove R up to that side, divide by M, take M down to that side, and I end up with V is BQR over M. Next, we're asked to calculate the flux density of the magnetic field needed to keep the proton in a circular orbit of that radius, and we're given a time for one complete orbit. So essentially we're just going to use the equation we've just been asked to show. The only complication is we need to work out the speed. It's very straightforward, 2 pi r upon period. We get that value for the speed, lob that number into that equation along with the other data we need. Charge on a proton is the elementary charge. There's the radius in meters. There's the mass of the proton, so you do have to do a fair amount of using your data book there. Lob that all in and you end up with a rather large magnetic flux density of 3.28. And then finally is what's actually a bit of circular motion. So again, we're looking back to G484, a bit of circular motion thinking. Explain why the magnetic field does not change the speed of the protons. So the key point is that force is always perpendicular to the velocity. Fleming's left-hand rule, as the velocity changes, the force changes, they remain perpendicular. That therefore means that it's not doing any work. Work done is force times distance moved in the direction of the force. Well, there is no movement in the direction of the force, no work done. So the kinetic, if there's no work done, there's no energy exchange. So the kinetic energy doesn't change, therefore it carries on at the same speed. So the two key points, force done is perpendicular to velocity, and therefore no work is done. That's G485 homework booklet question 8.